of the axial deformation of quadrupole moment. And after that, one performs angular momentum and particle number projection to get these blue curves. And finally, to take into account quantum fluctuations, the generator coordinate method is used to perform configuration mixing, and one obtains a spectrum and transition probabilities that can be compared directly to data. Now, of course, this approach is not limited to axial symmetry. One can also consider larger variational spaces for projected GCM calculations, in which, for example, triaxial solutions are projected on angular momenta, and the GCM is used to calculate spectra and compare them with data. Now, as an alternative, one can also, especially for heavier nuclei, one can also consider collective Hamiltonians, microscopic collective Hamiltonians, either quadrupole 5-dimensional collective Hamiltonian or Hamiltonians of higher dimensions, if also, for example, octupoles are included. And they describe nuclear excitations which are determined, in this case, by quadrupole vibrational and rotational degrees of freedom. The entire dynamics of this collective Hamiltonian is then governed by the functions of collective variables of collective deformation, the collective potential, the mass parameters, and the moments of inertia. Such a Hamiltonian is microscopic in the sense that it is completely determined by the choice of the underlying density function. Now, these are the models that can be used to describe shape coexistence and shape transitions. And my first example is shape coexistence and transitions in the n = 28 isotons. Now, in stable nuclei, the n = 28 isotons should be spherical because this is a neutron magic number. But this is not longer the case in neutron-rich nuclei. And the first indication of the onset of deformation is the neutron gap at the spherical configuration. The spherical gap is strongly reduced starting from calcium-48, where it's almost 5 MeV, and this nucleus is, of course, spherical. And then it's reduced by more than a factor 2 once one gets to magnesium-40, which is a neutron-rich nucleus. Now, these calculated gaps can be also compared with data, and you see that this is in qualitative agreement with empirical values of the gaps. What is shown in these figures are the single proton, single neutron and single proton levels on closed contours in the beta-gamma plane. And of course, if the spherical gaps are small, the nucleus will find a region where the gaps are large in the deformed region, and the deformation will occur. So in this case of argon-46, the gap for neutrons, so the curve here goes this way, and we can follow the levels through the beta-gamma plane. And for neutrons, the largest gap is at the spherical configuration, while for protons, the largest gap is at gamma = 60 oblate, and therefore one finds this very soft surface between spherical and oblate shapes. Now, 2 protons less, and we go to sulfur-44, and now for neutrons, the largest gap is at the oblate side, while for protons, it's on the prolate side, and so therefore we find shape coexistence. It's a very simple picture, and now you already see what is going to happen if this is of course the Fermi level, you already can guess what is going to happen if we decrease the number of protons by 2, then the gap is here. So then in silicon-42, both for neutrons and for protons, the largest gap is found on the oblate side, and of course, silicon-42 is an oblate nucleus. Now, starting from this self-consistent solution, one can construct the corresponding collective Hamiltonian, diagonalize it, and obtain spectra that can be then directly compared to data. For the example of coexisting shapes in sulfur-44, here is the the calculated spectrum, which can be compared with the available data, both the excitation energies, B2 values, and also the E0 transitions. Going to slightly heavier nuclei, an interesting topic is the evolution of triaxiality. There has recently been a report of empirical evidence of rigid triaxiality in germanium-76. So what is shown here are, again, the deformation energy surfaces in the beta-gamma plane for the germanium isotopes, and we find a weakly deformed triaxial shape in germanium-74 and much softer in germanium-76. And then eventually, for heavier isotopes, the shape will become spherical. Now, again, the collective states can be compared to data. Here is the energy ratio of the first two excited states, 4:1 to 2:1, and also the B2 values of the lowest transition. And the general trend is reproduced for the excitation energies and slightly less for the transitions. And in particular, we have then compared the nucleus 76 germanium, so the calculated Yeras ground state band and the gamma band is compared to experimental sequences. Now, the evidence of rigid triaxiality must come from the gamma band. And this is found in the level of K-mixing, which is reflected in the staggering in energy between odd and even spin states of the gamma band. So this differential quantity quantifies the displacement of a particular level with respect to the average of its neighbors. So for a deformed soft potential, gamma soft potential, then S of J oscillates between negative values for even spin states and positive values for odd spin states. In the case of the gamma rigid triaxial potential, this quantity behaves in the opposite way. It's positive for even spin states and negative for odd spin states. So here is the result of the calculation, and the data for 76 germanium are shown with these yellow triangles. For 74 germanium, we indeed find that this corresponds to rigid triaxiality, even though the amplitudes are relatively small. The heavier isotopes 78 and 80 are definitely gamma soft, and 76 germanium is in a transitional region. There is almost no staggering, and this is also the prediction of the calculation, which reproduces the trend and shows that actually there is no evidence for rigid triaxiality. So the conclusion here is that the mean field potential of germanium-76 is gamma soft, and then the inclusion of collective correlations drives the nucleus toward triaxiality, but is simply not strong enough to stabilize the triaxial shape. In heavier nuclei, an interesting phenomenon is the evolution of reflection asymmetric shapes, pear-like shapes. And so what is shown here is an example of axially symmetric deformation energy surfaces in thorium isotopes in the beta-2, beta-3 plane. So beta-2 is on the horizontal axis and beta-3 on the vertical axis. So starting from thorium-22, this is almost a spherical nucleus, very small quadrupole deformation. But then as we add more neutrons, you can clearly see how the octupole minimum develops. And it's strongly pronounced in 226 and 228, and then it becomes much softer. And the whole potential would correspond to octupole vibrations. This is, in fact, reflected in the calculated spectrum. First, the positive, of course, the octopole shapes are characterized by k equal 0 minus negative energy states. And for the positive parity states, they all decrease in energy. These are the Eras positive parity states. The open symbols are data. These lines are results of calculation. They decrease with mass number. And this reflects the increased quadrupole collectivity, quadrupole deformation of this nuclei. On the other hand, the negative parity sequence, which starts with 1 minus, these states show parabolic behavior with a minimum at about 226. And this parabolic behavior indicates that first the octopole deformation becomes more pronounced, and then the softness of the potential here means that we go from octopole deformed to octopole vibrations. Just to give an idea of how of the details of the calculation, this here is the spectrum of thorium-226, in which not only excitation energies but also transitions, E2 and E3 transitions are compared with available data. In general, E3 transitions are reproduced very well, slightly less for the E1 transitions. Now, in thorium, actually, one can even consider simultaneous quadrupole and octupole shape phase transitions. This is the same picture as I have just shown, but now for thorium, this is the energy surface in the beta gamma plane, and at the same time as a function in the beta 2, beta 3 plane. So 220 thorium is a spherical nucleus. 228 has a pronounced octupole minimum. But now in 224, you see that both in the quadrupole plane and also in the octupole degrees of freedom, the potential is soft, is extended, it has extended minimum, and it's soft. Now, soft extended minima allow fluctuations. Fluctuations, of course, mean there could be a phase transition, but of course, in a finite system, a phase transition will be smoothed out. Nevertheless, one can expect some signatures of phase transition. And this is also reflected in the probability density distribution of the 0 plus states, of the ground state, in which you see clearly the spherical case in 220 thorium, and then how the octupole degree of freedom develops, and then finally here in 228 we have stable octupole deformation. A signature of quantum phase transition is, of course, sudden change in the order parameters. So what is shown here observables and quantities that can be related to order parameters and how they change with the number of neutrons. So this is the ratio of the first two excited states, the expectation values of the deformation parameters beta 2 and beta 3. And you can see that they both show a sudden increase at n equal 134. Also, if we consider the B2 values and the B3 values in the negative parity sequence, the excitation energy of the second 0 plus state, and also the difference in the charge radii, in the ground state charge radii, all these quantities show this sudden jump at n equal 134, which can be considered as a signature of phase transition between, for the quadrupole and octupole shapes. A final example is the extrapolation now to very heavy and super heavy systems. In this region, the energy density functionals and the corresponding structure models are applied to a region which is far from those in which the parameters are determined by data, so one can expect that there are uncertainties in model predictions. In this region, of course, there is a much higher density of single particle states close to the Fermi energy, and therefore the details of the evolution of the formed shells with nuclear number will have more pronounced effects on the energy gap, separation energies, Q alpha values, band heads in ODE nuclei, K isomers, and so on. There is, of course, a much stronger competition between the attractive nuclear interaction and the long-range electrostatic repulsion, and this will produce more pronounced effects on the Coulomb surface and isovector energies. So one can expect fast shape transitions and, in some cases, exotic shapes. And in fact, most macro, micro, and microscopic HFB, and here also two HFB calculation, the relativistic calculation, they predict strong shape variations in this region. The color code, of course, correspond to different deformations. From blue would be oblate, and then red is prolate, and then yellow is spherical, green is gamma soft, and so on. So here one finds regions of very strong prolate deformation, but also exotic shapes which could develop, and all models agree that above n equal 120, one could even have super deformed oblate shapes. I will just show an example in the region of transactinides where there are spectroscopic data available. In this region, energy gaps are small, and therefore shape stabilization depends on how fast the shell structures vary with deformation. For example, if one considers the neutron and proton shell gaps, here is the neutron shell gap as a function of proton number and proton shell gap as a function of neutron number. In both cases, they show maximum at Hassium-270. Which in this sense can be considered as a deformed doubly magic nucleus. But notice that these gaps are small. This is of the order of 2 MeV, while before, when I have shown, for example, in Katsu-48, where this gap is almost 5 MeV. Now, the deformation energy surfaces, for example, for Hassium isotopes, shows this transition from strongly prolate shapes to 66, and then toward shapes with these energy surfaces become more soft in the gamma direction, and then eventually they would become spherical. Now, starting from the self-consistent solutions here, we can construct the collective Hamiltonian, diagonalize it, and follow the evolution of observables that characterize these phase transitions. Now, what is shown here is the ratio of the excitation energies of the first two excited states, 4-1 and 2-1, as a function of the neutron number, and also here the ratio of the reduced transition probabilities for the two lowest transitions. And this is for the isotopic chains of nobelium, rutherfordium, seaborgium, hassium, and darmstadtium. And then you can clearly see how in this region 158, 160, 62, these are perfect rotors. The ratio for all of them is 3.3, and the ratio of the transition probability is 143, 144. And then as you increase the number of neutrons, they become softer, and one can clearly follow this trend of how gamma softness develops, and then eventually toward n equal 180, spherical shapes would develop. This brings me to my conclusions. The evolution of shapes, shape coexistence, and shape phase transition presents universal phenomena that reflect the organization of nucleonic matter in finite nuclei, and they, of course, they can be found in every region of the mass table. The framework of energy density functionals enables a unified microscopic description of the structure of stable and nuclei far from stability, and also reliable extrapolations toward drip lines. And when this framework is extended to take into account collective correlations, then universal energy density functionals can describe deformation, shape coexistence, and shape phase transition phenomena associated with shell evolution. And as a final remark, all the examples that I have shown here, starting from n equal 28 to super heavy nuclei, have been calculated with a single energy density function, so not a single parameter has been changed for in all these calculations. Thank you for your attention.
Questions?
So would the novel energy density functionals in development now, would they impact on many of the physical features you highlight here today?
There are new energy density functionals which are being developed, which have a better microscopic foundation. This is one direction, but also there are those that are adjusted by also taking into account shell effects. The functional that has been used in this calculation here has only been adjusted to masses. So only masses have been used, no radii, no deformations, no single particle structure. So it's just about 60 masses have been used to adjust this, this functional, plus, of course, pairing parameters.
Okay. More questions? So, Dario, in nuclei like thorium-220 or 222, in which you see both gamma softness and octupole softness in calculations, shouldn't you expect to see triaxial octupoles as well, because gamma deformation breaks K quantum number, so you might have other octupole deformations.
Yes. What we find is that the potential energy surfaces become also soft in the gamma degree of freedom. But of course, to obtain a quantitative description of these spectra, one would need a framework that can take into account both beta, gamma, and octupole degrees of freedom, and this is multidimensional Hamiltonian or GCM, which is difficult to apply.
At this point?
Yeah, at this point.
Okay.
I was just wondering, for a non-expert in the field, the predictive power of this with respect to super heavy elements, as well as probably neutron-rich isotopes that are relevant for FRIP or FAIR or so. Is that controversial, or is it well established? And are there alternatives, or is this really the way your field looks at it now? Is this predictive?
Well, an alternative, of course, is to use effective interactions which are maybe microscopically based and perform configuration interaction calculations like shell model. But in that case, the problem is if you want to extend, many of these local approaches are determined by the data. And so if you want to extend this to regions where there are few data, then it's difficult to determine the model. This approach, as not only nuclear physics, but of course in atomic physics, in molecular physics, in solid state, the principal idea is that once you have an effective interaction among the particles that you consider, whether these are electrons or nucleons in nuclei, then the functional itself can be applied to any system that you might want to consider.
Still, a very important direction is to basically to base those density functionals in QCD through chiral interactions, which were discussed yesterday. So this is something which field is strongly pursuing now. Yes, Maria.
Yeah. Thank you. shape coexistence are levels quite close in energy. Do your model predict shape mixing in the ground state, for instance? There are some indications that appear in the krypton case. Do you have?
Of course. We have calculated krypton. This is just, I haven't shown this, this example here. But once you have the collective wave functions, then you can clearly see how already in the ground state, and especially in the excited states, how the probability density distributions of these collective states, how they are extended over different deformations. So you might think that you start from, for example, from a prolate well, and then you go to an oblate, but then as soon as you increase, even in the ground state, but as soon as you increase angular momentum, the probability density distribution will mix both configurations.
Okay, well, thank you very much, Dario, for a very nice overview and perfect timing. And the next speaker is Kazuhiro Yabana from Center for Computational Sciences in Tsukuba, Japan. And the talk will be on time-dependent Hartree-Fock calculations for multi-nucleon transfer and quasar fusion processes.
Okay. I'd like to talk on time-dependent Hartree-Fock calculation. So the energy density functional approach, not for structure, but the reaction. And for multi-nucleon transfer and quasar fission processes. And my work is under collaboration with my former student, Kazuyuki Sekizawa. He is now a postdoc in Warsaw Tech. Okay, you may know well that time-dependent Hartree-Fock is it's a theory to describe nuclear dynamics without any empirical parameters specific to system or dynamics. Just taking energy functional, then it's we get some definite results. And this is the basic equation. The dynamics is described by single-threaded determinants. That is the one restriction. And there are two kinds of applications of this TDHF approach. One is the nuclear giant resonance. That is in the regime of linear response approximation, and it's also called the random phase approximation. And the other is the nucleus-nucleus collision at low energy. So it's a nonlinear dynamics, and it's an initial value problem. And yeah, now it's now possible to make a realistic and systematic calculations using such TDHF approach, mainly thanks to the development of computers. So we can use now the complex and accurate energy functionals and free three-dimensional calculation and systematic calculation for various phenomena, including the fusion, transfer, and so on. So I'd like to also mention that the TDHF, or recently also we say the TD-DFT, time-dependent density functional theory, that born in nuclear physics, but now it's a very common and popular method in other fields. So I show here the statistics from the Web of Science. It's a number of papers with the keyword of TD-DFT or time-dependent density functional theory. So the words appeared 1982, but now the number of papers published a year is about 1,300. So yeah, I believe only the nuclear physics paper is only a few percent, mainly the chemistry paper. But anyway, in nuclear physics, it's a long history. It's a fusion reaction of very early calculation of two oxygen nuclei. It's a 78. And now it's one example, applications in laser optical sciences. That is the electron dynamics induced by laser pulse is described by time-dependent density functional theory. Okay, today I'd like to talk on the application of this TDHF for low-energy nucleus-nucleus collision, producing binary fragments. That's the multi-nucleon transfer reaction and also Kesai fission reactions. These reactions are recently getting much interest, for example, to produce super heavy elements or some unstable nuclei related to the third peak of our process, that the production of such nuclei is difficult by other methods. But the reactions of this transfer or Kesai fission dynamics depends very much on the type of the reaction. I mean, for peripheral reaction, it's transfer occurs as a succession of exchange of single nucleons. But as the impact parameter decreases, then we find a reaction forming a neck, and the neck breaking gives the transfer reaction of multi-nucleon transfer. And at the small impact parameter, we have a fish fusion, but when the heavy nuclei comes in, then Kesai fission dynamics also appears. So, okay, let me first tell about the description of multi-nucleon transfer by time-dependent Hartree-Fock. So I choose one specific reaction, nickel and lead 208 at the energy of 328 MeV. For this reaction, there is a measurement of the multi-nucleon transfer some time ago. For example, here, the 6-proton transfer from nickel to lead seen here, and the 8-neutron transfer from nickel to lead is seen here. So I'd like to show how the TDHF describes the reaction cross-section of this transfer reaction. So it's a calculation, density profile of the calculated collision. This is at the impact parameter of 4 femtometer. That's a large impact parameter. So this is the initial configuration. The 2 nuclei comes close, but because of the Coulomb barrier, there is only a few nucleons exchanged at this stage and finally divided into 2. Even with such collision, 1 or 2 nucleons are exchanged, so it's a peripheral collision. And at small impact parameter, it's 1.6 femtometer. So once the thick neck is formed, and then neck breaking gives some transfer of nucleons. So, okay, this is the average number of exchanged nucleons and the total kinetic energy loss as a function of the impact parameter. This is the calculation of time-dependent Hartree-Fock. So we can see there are 2 impact parameter regions that the reaction dynamics is rather different. So at the impact parameter larger than about 2.5 femtometer, so you find the neutrons are transferred from positive, means from lead to nickel, and the protons transfers to opposite direction. So it comes from the Q value problem. So it's a charge equilibrium. So, but inside this distance, from below this 2.5 femtometer, the neck is formed during the reaction. Then you find both neutrons and protons are increasing. That means the neutrons and protons are transferred to the same direction. That means okay, once neck is formed, then neck is broken. So the neck part goes to one nuclei. Then both protons and neutrons are transferred to the same direction. So, and also, once a neck is formed, we find a large energy transfer from the relative motion to the internal excitation. Okay, so we get such reaction dynamics, and we get the final fragment nucleus in the TDHF calculation. But okay, in the TDHF calculation, always we treat the single threat determinant, and the number of total number of nucleons are of course conserved. But the wave function after collision here, it's not an eigenstate of the number operator in specific spatial region. So it's in each region, the wave function is a superposition of different number of nucleons. So we can, to evaluate the cross-section from the TDHF calculation, we need to know the transfer probability as a function of the impact parameter. And it's possible by making a projection operator technique that's recently proposed by Simenel. It's an efficient way to evaluate such probability. Then we can calculate from the TDHF wave function after collision, we can get the transfer probabilities as a function of impact parameter. Here, it's the neutron transfer probability as a function of impact parameter. So it's from 0 to 6 to 7 to 13. It's a rather central collision. But okay, anyway, we only find a transfer from lead to nickel. So neutron transfer probability from nickel to lead is vanishingly small. For the case of proton, we find a transfer of nucleons in both directions. Negative is the nickel to lead. So once we get such probability, we can calculate the cross-section by integrating over impact parameter. So it's a comparison of the cross-section with the experiment. So looking the cross-section, this is a zero proton. So proton is not transferred, but the neutron is transferred from lead to nickel. So 1 neutron, 2 neutrons, small number of transferred nucleons. The cross-section is rather well described. But as the number of transferred protons increases, the cross-section is underestimated by the calculation. And also the peak position of the neutron is shifted. So, but it's evaluated just after the calculation of the time-dependent Hartree-Fock. So the final nuclei is still highly excited. So afterwards, there should occur neutron evaporation with a much longer time scale. So next thing we need to do is the estimation of the slow neutron evaporation by statistical model. So for that purpose, we need to estimate how much excitation these nuclei are. And for that, we develop projection. We calculate the energy expectation value of each fragment with the number projected wave function. So from such procedure, we can estimate the excitation energy and how many nucleons are evaporated. So this is the result after estimating the evaporation of nucleons. So blue curve is the after taking into account the evaporation of nucleons. So it shifts beta direction to the to coincide with the experiment, but still we cannot explain the cross-section of the transfer of many protons and many neutrons. So it indicates some limitation of the such time-dependent Hartree-Fock approach for the transfer process. So let me summarize the this part of my talk, the TDHF calculation for multi-nucleon transfer. So using the projection operator method, we can evaluate the cross-section and compare with the experiment. And the TDHF seems to describe reasonably the cross-section for a few nucleon transfer processes, but it underestimates the large transferred nucleons. So the success and failure looks similar to the empirical calculation of grazing or CWKB. That is the some direct reaction model assuming a single nucleon, successive exchange of single nucleons. So it's a comparison with the calculation by several methods. So red points are experiments. This red line is our TDHF calculation for zero proton and neutron transfer and zero neutron and many proton transfers. And the CWKB is one of the direct reaction type approach. So it looks very similar to the time-dependent Hartree Fock. So it's, in some sense, reasonable because the time-dependent Hartree Fock assumes mean field type dynamics. And the direct reaction type approach assumes successive transfer of single particle motion. So Langevin approach describes something better. But of course, we should keep in mind that there is a well-known drawback of the TDHF, that the variance is underestimated substantially by TDHF. That is well known for a long time in the analysis of deep inertial collision. So in our case, we get the probability. So average number is given by this expression, but the variance is given by this one. So variance is underestimated in TDHF, and this, to some extent, explain the failure of the many nucleon transfer in the TDHF calculation. Okay, next, I'd like to move to the analysis of the Keisai fission processes. So the Keisai fission is the process of fission that takes place before reaching full equilibrium of the collision of heavy nuclei. And that is seen for fusion of heavy nuclei with the charge product more than 1,600. That is the, we expect a fusion hindrance. And for this Keisai fission, there are many discussions related to the nuclear structure effect. For example, the shell effect becomes important in such Keisai fission process, or this process is very sensitive to the orientation of the deformed nuclei relative to the nucleus-nucleus relative motion. And also it's attracting much interest to produce super heavy elements or other unstable nuclei. And actually, there are recently several papers discussing the Keisai fission processes by time-dependent Hartree Fock, and they report a successful description of the time-dependent Hartree Fock for this process. So let me take one example of this paper. So in this paper, its title is the interplay between quantum shell and orientation in Keisai fission. So this is an experiment and theoretical TDHF analysis of calcium and uranium nuclei. And it's a tip collision. Tip collision means the collision of the prolate deformed nuclei in this direction. And the side collision is the prolate deformed uranium is in this direction. So low energy reaction is dominated by this tip collision, and the high energy is by the side collision. And also it's time required for the Keisai fission is very different between these two collisions. So the very fast collision in tip case, and in that case of tip case, the final fragment becomes very close to the proton number 82, so it indicates the importance of the magic number. But for side collision, it's almost half and half, so it's gets a long time. So yeah, I'd like to show our calculation of the TDHF calculation for other systems. First example is the collision of uranium and the tin-124 nuclei. Okay, for this system, there is a measurement of the cross-section long time ago, about 30 years ago, and there was an observation of the many nucleon transfer from uranium to tin nuclei. The transfer of about 15 protons and 10 neutrons are seen in the measured cross-section. So let me show how the TDHF calculation for such collision. Okay, this is a side collision, and this is a tip collision. So it is, in some sense, opposite to the previous published paper. In this case, the side collision finish faster than tip collision. And in side collision, we observe a very small number of transferred, average number of transferred proton and neutron. Only one proton, one neutron is transferred in average. But for tip collision, we observe many transfer, 7 protons and 11 neutrons. So actually the number of transfer, the nucleon, very much depend on the orientation in this system. So this is a cross-section we evaluate from the probability. So then, okay, for this tip collision, as I said, there are many protons and neutrons transferred. But for side collisions, we observe very few. Okay, after including the effect of evaporation, basically it's similar. So, okay, comparing with the experiment, our calculation indicates that the transfer of many protons and neutrons observed in the experiment that comes from this tip collision. That is our conclusion for this reaction. So, okay. As a final topics, I'd like to discuss quasi-fiction dynamics with the, okay, systematic view of the quasi-fiction dynamics, changing energy and impact parameter. Okay, so this is the same system and the head-on collision and changing the incident energy. So the 5.7 MeV that the experimental analysis was made is here. So at this energy, the proton and a neutron and proton are both transferred in natural direction, normal direction. Normal means the mass equilibrium direction. And also the number of nucleon exchanges is very small for the side collision, green one. But as the incident energy gets higher, we observe the inverse direction. That is the, this is a so-called inverse quasi-fission. So the direction of the transfer is not from large to small, but the small to large. So our finding here is that at higher energy, the inverse quasi-fission occurs for this system. So let me see why the transfer occurs in inverse direction. So this is the low energy case, and this is the high energy case when we find an inverse quasi-fission. So because the energy gets higher, we get some internal excitation energy, more internal excitation energy. And here you find there are some density fluctuation. And density fluctuation gets the neck here and makes a fission, making a smaller fragments here. So it seems it's related to the density fluctuation of this dynamics. So let me show the animation for this dynamics. So at higher energy, there is some density fluctuation that makes the neck here and makes a quasi-fission in this system. So let me show once more, because it's usually not easy to. Okay. Okay, anyway, density fluctuation makes the appearance of the inverse case efficient. Okay, let me show another view. This is a different system, but anyway, it's a systematic calculation of various energy and also impact parameter. So it looks very complicated. This is the inverse case efficient, and this is a normal case efficient. But if we plot it against this quantity, this is the closest approach distance in the Rutherford trajectory, then it's a very simple structure. So the changing the energy and the impact parameter, the dynamics is very simple if we view as a function of the distance of closest approach. That means actually the angular momentum is not important, but the radial direction, actually symmetric direction is important. So we find a normal case efficient for this system, and again, at higher energy, it's inverse case efficient. So the appearance of the inverse case efficient is not specific to some system, but also it seems always we find for some higher energy case. Okay, let me summarize my talk. So I discussed the application of TDHF for nucleon transfer processes of multi-nucleon transfer and case efficient. So it's I think it's a fruitful approach to propose appropriate reaction producing superheavy elements or other process nuclei. But of course, the theory lacks the description of correlation effect. So the theory beyond the mean field is, of course, always important. Okay, thank you very much.
Thank you very much for this nice overview. Questions? Yes, here.
So quasi-fusion is a process characterized by a broad mass distribution, mass and charge distribution, that involving a broad range of mass charge partitions. You are talking about a mean trajectory approach. It is nice to see this development, but in my view, development beyond time-dependent Hartree-Fock calculation are needed to really describe or address quasi-fusion phenomenon. What do you think about that?
You mean the case efficient requires description other than
multi-configuration calculation? So you have a time-dependent Hartree-Fock. You have only one mean field, one Slater determinant, and a mean trajectory. And quasi-fusion is characterized experimentally and also theoretically, to my knowledge, by a broad mass and charge distributions. So you have a lot of mass charge partitions. Yeah. And you showed before that if you have six proton-neutron transfer, then the description of time-dependent Hartree-Fock is poor, is not very good. So my view, my question is, do you think it is needed development in theory beyond time-dependent Hartree-Fock calculation to address this phenomenon or not?
Yeah, of course, yeah. My answer is, I think the TDHF for case efficient has some reasonable meaning. So of course, there are many final products for the same reaction, but it's a superposition of many impact parameters. So if the mean trajectory is dominated by single, so the many fragments comes from the different impact parameters, then the time-dependent Hartree-Fock calculation gives a reasonable description. And actually, the recent analysis seems to provide a reasonable description for the gross future of the case efficient.
Yes. I'm asking Hamiltonian. You have Hamiltonian, just the sum of two fragments, or any nuclear, which are linked with the other proton or neutron, which belong to fragments. So what is your Hamiltonian? It's just a simple sum of the two fragments, Hamiltonian, or?
Yeah, just we solve the time-dependent Hartree-Fock, then they automatically separate two.
Yes.
So it's if we divide by two space, both we have a Hamiltonian for projectile and the target. So of course, Slater determinant single particle wave function is extended to both nucleus. that makes the various probabilities of various nucleon distribution from the single-threaded tangent.
Yeah, it's great to see the ability of DFT to get cross sections. Yeah. So there will be, of course, a lot of progress in years to come. So tell me, is pairing at this point in the picture or not?
No, this is just a TDHF, so we never include the pairing.
You never include pairing, yeah. Okay, well, I'll thank Yabana-san again. And the next talk is by Silvia Leoni from Milano on interplay between collective and single particle excitations around neutron-rich doubly magic nuclei.
Ok? Do you hear me? Yes. E questo anche, mamma mia. Okay. So, good morning, everybody. I'm very pleased to be here to this very prestigious conference and to present my work. So I'm going to discuss about interplay between collective and single particle excitation around neutron-rich doubly magic nuclei. And I will start with a brief introduction about different theoretical models which can be used to describe excited states in nuclei. And then I will go through recent gamma spectroscopy data obtained around doubly magic nuclei in different regions of a nuclear chart, in particular around the doubly magic calcium-48, T132, and lead-208. What do you need? Okay. Test. Complicated. Okay. Okay, so data were taken around these regions with different in different experimental campaigns. I will explain you later. So this topic is strictly connected with one of the greatest challenges in modern nuclear physics, which is the quest for a unified description of all nuclei along the radionuclide mass table, and from light to heavy, including the known stable and unstable nuclei we know on Earth, and going also to the more than twice unexpected nuclei we believe existing in the universe for more than 6,000 isotopes altogether. So the challenge, it's easy to understand, because if we focus for a moment of shell structure for both protons and neutrons, we see immediately that if one wants to describe microscopically the structure of these nuclei by placing nucleons in the orbitals, then immediately one finds that the number of configurations to be taken into account explodes. It becomes very huge, already around mass 100, and we are down here. We have to deal with 10 to the 28th different configuration, which make the problem really a computational challenge. And this is the reason why only for a very limited number of nuclei, smaller than mass 50, it is possible nowadays to perform ab initio calculation in which one starts from taking into account interaction between nucleons derived by the chiral effective field theory, while for the vast majority of the remaining systems, one has to deal with other approaches, like, for example, shell model calculation, which even when they are very extended, they have to do truncation in the computational scheme to overcome these difficulties. And, for example, they can be performed at the moment only up to mass 100 or around closed shell with frozen cores. And in the future, the hope is that by the approach described by Dario Vretenar in the previous talk, the energy density functional, one could have a more general description of over the entire nuclear chart. So now if we come back for a minute to shell model, microscopic description, then the main idea behind this approach is even with large scale nowadays, is to assume some truncation scheme, which is basically done in a way that you describe the nucleus as a frozen core, which is usually a doubly magic system like calcium-40 or lead-208. And one treats the interaction among valence nucleons only outside of the core. And these are usually extended over one or at most two major oscillator shells, depending on the mass we are dealing with. And we see immediately the limitation then, because then, of course, this is very nice for interaction among nucleons, but when one has to deal with core excitation, especially complicated core excitation involving many nucleons at the same time, these type of excitations are not considered in the shell model description. And this is a problem, especially when we are around doubly magic nuclei, where phonon excitation, for example, 2+, 3-, and 4+, becomes very important and dominant in the low energy excitation spectrum. And as a consequence, all nuclei around doubly magic nuclei, 1 and 2 nucleons away from shell closure, they are also expected to be strongly influenced by this type of couplings of particles outside the closed shell to the core excitation. And this type of excitation, which is called particle phonon couplings, are key ingredients for a series of very important phenomena, like, for example, the quenching of spectroscopic factors, the harmonicity of vibrational spectra, all damping mechanisms all the way to giant resonances. So it's very important to study them in details. And up to now, the main theoretical approach was based on phenomenological description developed many years ago by Borem Ottesson in the region of lead. But since the problem is very relevant and interesting, now there are several microscopic attempts done by various groups to try to describe in a more consistent way microscopically this phenomenon. And of course, we need experimental information to validate the theory and to stimulate further development. So the idea of my talk is to present you a survey of experimental results we obtained in recent years around calcium-48, Tin-132, and lead-208 with different experimental setup, trying to search for this type of particle phonon excitation and to stimulate theoretical development. So we start with the calcium-48 region. Here we are at the value of stability. These nuclei around calcium-48 are very tough to be studied experimentally because they cannot be reached by conventional fusion evaporation reaction. So a lot of work was done in the past by the Krakow group, which pioneered this technique of multinucleon transfer reaction with SiC target. And this is an example of a spectrum of calcium-48 obtained, where we see that among the first excited states, we have a 3- octupole excitation, which has a sizable collectivity, 7 Weisskopf units, while in this case, the 2+ is very little collective. So if we now go to study calcium-49, this is also obtained by the Krakow group, then you see that the excitation spectrum, besides having single particle states, has also a complex structure where one expects to see candidates for coupling between the neutron and the octupole phonon. So the idea was to study further this case and to have a firm indication of this type of excitation. So we did an experiment some years ago in Legnaro National Laboratory, making use of a prisma spectrometer constructed by Alberto Stefanini, Giovanna Montagnoli, Enrico Fioretto, who are also here. And at that time, the spectrometer was coupled to a large germanium array, Clara, and this is ideal when one wants to study multinucleon transfer processes, binary processes, in which a large number of reaction products are populated at the same time, so they can be very well identified in the spectrometer, and for each of these reaction products, due to the coincidence with the Clara array, germanium array, one can do spectroscopy, gamma spectroscopy. And this is this type of configuration, a spectrometer coupled to a magnetic spectrometer coupled to a gamma spectrometer, has been used later by Agata, by the Agata array in Legnaro with Prisma, and is now used with exogam, later with exogam, and now Agata at Vamos in Ganil. So the result we had at that time for calcium-49, this is the clean spectrum measured in the germanium array, and this is the level scheme. So we could firmly establish spin and parity of some of the excited states, doing angular distribution, polarization measurement. And then later we did also a lifetime measurement by the differential plunger technique, which gave us confirmation that this state is not only a knife plus state, as we saw from this measurement before, but has a collectivity which is very similar to the one of 3- phonon in calcium-48, which means that this state is really a particle phonon state. It appears as the highest spin member, possibly, of a multiplet of states arising by coupling the unpaired neutron to the 3- octupole phonon in calcium-48. So to interpret this state at that time, there was not available a macroscopic model easily applied. So our colleagues in Milano, Gianluca Colò and Pierfrancesco Bortignon, they made a schematic calculation making use of this phenomenological model by Bore Motteson. And they first checked that the 3- in calcium-48 by RPA was giving a sizable collectivity compared to the experiment. And then they performed the calculation for the phonon coupling, and they had a splitting of the multiplet, as you see here, and a nice agreement for the energy of a 9.5 plus with what was found experimentally, and the strength has to be the same of one of the phonon. So now it's interesting to see what the shell model calculation can do in this rather light mass region, which is around 50, where they managed to get there, and these are calculations performed by Utsuno, who did calculation not including all possible configuration which are relevant because of a computational problem. So he managed to have some kind of calculation in a truncation scheme, and he obtained results for these 9.5 plus state, which are not very far. Also, the collectivity is 6 Weisskopf units compared to 7, which is not too bad. What he found is that the spectroscopic factor calculated was a little bit too high compared to some previous data, experimental data taken by another group. But altogether, it seems that at least up to this level, shell model calculation, they are almost able to do a good job. So the lesson we learned from calcium-49 is that we have evidence for a type of particle phonon state, which is well reproduced by phenomenology, and large scale model calculation, which are still doable in this region, are getting there, although we are not perfect, but we're very close to the experimental data. So now we move to the next region, which is thin, and this is much heavier than before, and this is where a shell model cannot go to describe this type of excitation because of the dimension of the space. So this thin region, we are now away from the value of stability. It is a doubly magic nucleus. We know that the excitation spectrum of tin under 32 is dominated by this phonon excitation 2 plus, 4 plus, and 3 minus, which are rather similar in collectivity. And we expect also that if you look at antimony, 133, now we are 1 proton away from core, the excitation spectrum, which was known from decay after the isomer, this long-lived isomer, shows, apart from single particle excitation, also a large number of states which one should be able to relate to this kind of phonon excitation from the core. And we would like to investigate this further. So experimentally, this is not simple, because in this region, there are a lot of, this region is characterized by several long-lived microsecond isomers, which makes the spectroscopy above the isomer very, very difficult. So there are basically no information above the isomer from experimental studies. So new data about antimony came from a recent campaign performed in Grenoble at the reactor, which is a very nice place, because here we have a world brightest continuum neutron source delivered with 10 to the 14th neutrons per centimeter square per second. And then there, a couple of years ago, it was constructed a dedicated beamline which was focusing these high-intensity neutrons down to 10 to the 8th intensity with a highly collimation. These are cold neutrons now. The size of the beam is 1 centimeter square. And they were brought down to the experimental area where this setup was placed for the gamma spectroscopy campaign. And this is the setup. It was the first time a very large germanium array consisting of up to 52 germanium crystals was installed around a highly collimated cold neutron beam. It was used in 2 different versions. First version was a version for just gamma spectroscopy, conventional. So it was 10 clover from the hexagon array of Ganil, complemented by some germanium from the Italian collaboration for a total of 6% efficiency. And in the second part of the campaign, some detectors, germanium, were replaced by lanthanum bromide fast scintillators to allow fast timing measurement for lifetimes. So the acquisition system was fully digital and triggerless, and this to be able to sustain a high event rates up to 600 kilohertz with a time stamp of 10 nanoseconds, which gives really the opportunity to perform gamma coincidences over a very wide time interval of several microseconds, which is exactly what is needed when one has to look for coincidences from between below and above isomeric states. So data were produced by neutron-induced fission on uranium and plutonium target, and then there were also some short runs of neutron capture on several targets. So now this is antimony. This is what it was known before our experiment. The isomeric decay, the gamma decay after this very long-lived isomer. So we've performed the measurement, and by playing with coincidences on a strong transition, depopulating the isomer, and looking at what was seen in coincidence, impromptu coincidence over this wide range of time, we could see structures appearing up here, never seen before. So this is the population of the isomer from the top, and going probably all the way up to spin 25 plus. So now comes the problem of interpretation of the data. So apparently this looks like a multiplet of states, a positive parity from below to above the isomer. And now we made a lifetime measurement in this second campaign with these fast scintillators. We focused on these two states. And we found that from the lifetime, the BM1 transition probability associated to the decay from these states is very, very different. There are almost 2 orders of magnitude, even more differences in BM1 strengths, which means that these states are not simple at all. They cannot come for a simple configuration. They must be very complex, and we need to interpret them. So how do we do this? Because the shell model don't work. We are not able to perform calculation for this type of things, just to say that if you consider free particle, free Hall excitations, it takes weeks on a computer with 1 million processor to perform a calculation. So more complex configurations are simply impossible. So now we had some help from our colleague, theoretician in Milano, Gianluca Colò and Pierfrancesco Bontignon, who developed a model, they called it hybrid model, which is just an extended microscopic particle vibration coupling model, which works in the following way for antimony 133. So you start calculating the excitation of tin, the core, by RPA using a Skirm interaction, and they did it all the way up to 5.5 MeV. Altogether, you have something like 17 states. I'm just showing here the phonon excitation. They come up nicely. And then you have some additional states with much lower collectivity. Then you have to couple this core excitation to single particle proton states, also calculated by a trifoc with the same Skirm interaction. And this coupling is done in a consistent way because the coupling matrix elements are calculated consistently within the same scheme. So in a way, this model is a free parameter model. So these are the results obtained for antimony 133 from this approach. You have here the spin of the states and the excitation energy. So first of all, you get back, of course, the single particle stage, which is slightly modified compared to the unperturbed case. And then you have a very rich spectrum of states in excitation energy and spin, which turned out to be very much mixed, coming from all this configuration calculated. And if you compare with the experimental data, these are the states we measured in our experiment. They seem the lowest one, the ERAST, which are the only one known, are quite well reproduced. If you go into the calculation and you look, you see that the high spin members, which are the one just observed, they are coming from the same configuration, which is this proton coupled to this neutron particle hole in the core. While if you go lower in spin, this is where exactly we measure the lifetime, you see that in the calculation there is a strong component coming from the mixing with the phonon. So we believe that this model is quite appropriate to describe this type of states we measure. So if we summarize, we have measured something which cannot be described by the shell model calculation, but on the other hand, this gave rise to a new development, this hybrid model, which is able to take care of core excitation involving more nucleons than usually, and valence particles. So now I come to the last example, which is lead-208 region. And here, lead-208 is, of course, a very well-known nucleus, and it is characterized by a very strong octupole excitation, one of the strongest of the nuclear chart, 34 Weisskopf units, which means that all nuclei around this region are strongly influenced by this core excitation. And in fact, this is where, in bismuth 209, it was for the first time observed a multiplet of states arising by the coupling with the particle and the phonon in lead, which gave rise to the development of the particle phonon model by Borem-Ottelson. Now we concentrate on bismuth 210 instead. So we have one proton and one neutron outside the lead core. So this is a case which is ideal to study not only the couplings between valence particles, protons and neutrons, but also the coupling of these two valence particles with the core excitation, in particular the phonon of lead. So we got data from Grenoble again. This is neutron capture on bismuth 209. So generally, neutron capture works in such a way that you populate the capture state and then you decay statistically to almost all spin states available. And this is indeed what it was obtained, an impressive level scheme worked out by Natalia Czech-Pliczka during her PhD thesis in Krakow. So you have an enormous amount of transitions from the capture level, connecting all the states down. In red, you have newly found things. And they can be very well analyzed, for example, selecting high energy transitions in coincidence with lower line gamma transitions. And by analysis of angular correlation, which were made possible by the geometry of the array, it was also possible to determine for a large number of states spin and parity of the excited levels. So having such a rich data set, one can aim then to a complete low spin spectroscopy in this nucleus. And this is a comparison between the experimental data and the shell model calculation. This time, shell model calculation are done taking the core, lead-2As as a frozen core, and considering all correlation between the proton and neutron valence particles. So you basically have a one-to-one correspondence between the experimental data and the calculation. But if you look closer in this region around 2 MeV, then what you see is that there are some states which are not reproduced, not appearing in the calculation, and this is where exactly where one would expect to observe correlations, couplings between these proton-neutron valence particles and the phonon in lead-208, which comes exactly at 2.6 MeV. Yes, I'm finished, in this region. So, of course, this is a very good example of something which should be described in a more general framework, for example, making use of this hybrid model, which was developed for 14. So now, if I come to the conclusion, I have presented this problem of couplings between particle and core excitation around double shell closure. These are very important phenomena to study because they come in as key ingredient in several things, like, for example, spectroscopic factor quenching, damping phenomena, and they cannot completely be described by shell model calculation, especially when you go to the heavy system. So by presenting this survey of data around doubly magic nuclei, I showed you the evidence for several of these type of excitations taken in campaigns at different laboratories, which really offer the possibility to new development from a theoretical side. This is just an example of how one could expand the theoretical interpretation on a more general basis. Thank you. Okay, and this is, of course, the collaboration.
Thank you very much, Sylvia, in particular, for emphasizing the good coupling between experiment and theory.
Yes.
So, questions to Sylvia? Oh, yes.
You have calcium 49. You have there a 9.5 plus, which you say is the 3 minus and P3 half. Where are the other states, 7.5 and so on? Okay.
They could not be observed in this experiment I was showing because the reaction is not favoring the population of these states.
Why?
Because in this binary reaction, you usually tend to populate, to transfer the maximum angular momentum. And this is a known problem.
Okay. Yeah. Next question. What is the excitation energy of this 9.5?
The excitation energy, it was
yes, where is it?
4 MeV above ground. 4 MeV above ground state.
There is a single particle G9.5, not very far, I think.
Yeah, but...
you mix them? Do you mix this 0 plus G9.5?
But I mean, you mean it is observed, it is just close by and you can disentangle this.
No, I mean in the calculation.
No, in the calculation, well, for the phenomenological it was not done because it was simple. For the shell model, I think it comes natural from the extended shell model calculation.
No, but the two can mix because there is
yeah, but it was included in the calculation.
This is something to be discussed.
They had exactly this problem of including this G9.5 in the and they did it with some difficulties because of the phase space, but I mean, it was done. This was actually the point of the calculation, to show the importance of this.
Excellent. More questions to Sylvia? Yes, Frank.
I'm interested in your calculation with particle vibration coupling calculation. In many cases, for some scum force does not give very good single particle levels. So they want to improve the calculation with particle vibrations. So my question is, does this calculation give the good excitation energy for the isomers compared to data?
I mean, you are talking about this antimony now.
Yes.
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 The calculation, they are close to the data within 100 kV, something like that. But I mean, we know that we cannot pretend to be precise in energy with this approach. I mean, this is something which our friends in Milano, they like to stress, that you cannot really go and compare one-to-one. If you are within 100 or even 200, they are very happy, and it has to be consistent with all with the trend of all states. I mean, not just one. I mean,
100, we are very, very happy.
Yes, exactly. You can confirm. Yes.
Okay, let us thank Sylvia again. Now, two things. So next talk will be by Uesaka-san on from RIKEN on heavy ion charge exchange reactions. Immediately following this talk, there will be important announcement by Professor Spitaleri. So if you want to go to the trip tomorrow, you do not want to go for lunch now. Just wait, wait, because you will be sorry if you do not listen to what he wants to say. And Uesaka-san kindly agreed to talk to this side, to this screen. So this part of the audience is enthusiastic now.
Thank you very much. And first of all, I would like to thank organizer for inviting me to report our recent work with the heavy ion charge exchange reaction in Japan. I'm Uesaka from RIKEN Nishina Center, and I would like to discuss the power of a heavy ion charge exchange reaction to probe new aspects of nuclear spin and isospin responses. I organized my talk like this way. I will start with a very brief introduction to the nuclear spin and spin responses, and which is followed by the why we need a heavy ion charge exchange reaction for future work. Then I will switch to the more experimental work in Japan, which I use the Chirac spectrometer at RIKEN and the ground gradient at RCNP. And I will mainly talk on the two topics, which we use the heavy ion double charge exchange reaction. And we try to search for the double gamma stellar resonances and the tetraneutron state, which are very exotic. Okay, nuclear spin and spin response, which has the origin of the study of beta decay. Beta decay always accompanied with a change of isospin, and weak boson coupled to the nuclear spin very strongly. And because of this, beta decay tells us much about the nuclear spin and spin responses. And later on, people realize that nuclear spin and spin responses have much to do with the pion in nuclei. And in nuclear structure terminology, we can say we can learn much about the tensor force effect and the three nucleon force effect because those interaction is mediated by pion. And these nuclear spin and spin responses also have much to do with the nuclear matter properties. One of the good examples is the pion condensation. From the previous study on the nuclear spin and spin responses, we know that the pion condensation doesn't take place at the low densities. And this is mandatory for the existence of, say, two solar mass neutron stars. Okay, if pion condensation takes place at a low density, the nuclear matter cannot sustain a very heavy neutron star. This is one of the examples. And it has also to do with weak responses in the universe, in the for the understanding of supernovae explosion, we should know what is the electron capture rate and what is the beta decay rate and what is the neutrino responses in the supernova explosion. And our understanding, nuclear spin and isospin responses tell us what is the process is that. And another example is a double beta decay. We definitely need a precise nuclear matrix element. Okay, beta decay is a very good probe for the nuclear spin isospin responses, but it is in a sense limited. we can probe very low-lying states with beta decay because of the Q value. And the people started to use electromagnetic and hadronic reaction to probe the highly excited state, nuclear responses in a highly excited state. And among them, light ion induced charge exchange reactions, such as the PN reaction, helium-3 reaction, and the D-helium-2 reaction, have been most popularly used so far. And a rich amount of the data and the theoretical work have been made, and which are reviewed in a nice review paper in the literature. Okay, then now maybe I am allowed to say that our understanding of the nuclear gamostellar resonance, gamostellar transition in stable nuclei are not so far away from the satisfactory level. Okay, now sorry. Not recently, 20 years ago, this PN reaction studies have been applied to the radioactive nuclear beam experiment. And the first experiment was done by Teranishi at RIKEN. He tried to look at the isobaric analog state by PN reaction in lithium-11. And they have looked at the Coulomb displacement energy to look at the proton distribution in the beryllium-11, isobaric analog state of lithium-11 ground state. And technically, experimentally speaking, they used invariant mass spectroscopy, which is very nice. They can achieve a very good energy resolution. But at the same time, they are sensitive only to the low-lying unbound states only. This was the problem. Okay, and quite recently, this reaction, PN reaction technique have been applied to the, missing mass technology. Missing mass spectroscopy have been applied to the PN reaction studies with radioactive nuclear beam. What is good about this missing mass spectroscopy is that we can probe whole range of excitation energy, even a bound state or the highly excited resonance, giant resonance state, we can probe with this missing mass technique. The pioneering work was made in Michigan State University by Sasana and Degas, and they looked at spin-isospin response in nickel-56, which stays in the core of a supernovae explosion, and they concluded that the electron capture rate could be slower than expected from the measurement. Okay, and this PN technique has been introduced to RIKEN recently, and we have applied it to the wide range of nuclear charge from helium-8, beryllium-12, and tin-132, which will appear very soon. Now the data is still preliminary level, but it will appear soon. Okay, and here I would like to discuss a little bit about what should be the nuclear spin-isospin studied in the new era. Of course, the study of unstable nuclei is one way to proceed, but I would like to claim that another direction, extension of a nuclear spin-isospin study to the higher multipolarities, higher tones, and many multi-phonon states is really important. You know, say higher multipolarity, we need example is spin dipole resonances and higher tones, isobector spin monopole resonances, and so on and so on. But the data is really scarce for the resonances if you compare with the gamostellar resonances. It is because of the probe, which is relatively difficult to study those states with light ion induced reaction. Okay, then definitely we need a heavy ion charge exchange reaction. It is because this reaction has a unique capability which are missing in light ion induced reaction. I will list three capability of the heavy ion charge exchange reaction. One is the surface sensitivity. This is especially the case of the isobector spin monopole resonances, which is a higher tone of gamostellar resonances. And because it is a higher tone of the gamostellar resonances, its transition density has a node close to the nuclear surface. And if we use a light ion in this reaction, it penetrates deep inside the nucleus, and then the strong cancellation from the contribution from the outer side and the inner side takes place, and which results in a very small cross section. We cannot probe isobacter spin monopole resonances with the light ions. But if we use a heavy ion, it is a strongly absorptive, and we can probe only the surface, and which results in a large cross section, and we can probe the isobacter spin resonances with a heavy ion. This is one property of heavy ion charge exchange reaction. And the second one, it is a variety in transferred quantum number is available with a heavy ion charge exchange reaction. Say, it is a good contrast to the case of a PN and helium-3 reaction, which are limited to the spin and isospin transfer of 0 or 1. Okay, I will show you the example later. And the last one, which is available only with a radioactive nuclear beam, which with this reaction, we can control kinematic condition. More specifically, I will introduce a case of exothermic reaction with which we can excite a highly excited state in a recoilless manner. I will come back to this point later. Okay, let me claim that heavy ion charge exchange reaction can be a unique instrumentation to investigate new aspects of new spin isospin responses. And at present, experimental activities are ongoing in Japan and Michigan State University, and here, Catania. Okay, I will mainly discuss the activity in Japan, but let me shortly introduce you to the activity here, which is the project led by Francesco Capuzzello. They are trying to understand the double beta decay nuclear matrix element through heavy ion charge exchange reaction. And with a magnetic spectrometer, magnets, they have already get a very beautiful data. Okay, let me back to the activity in Japan. We use two spectrometers, two high-resolution spectrometers in Japan. One is Charac and another is Grand Leiden, and they are definitely needed for heavy ion charge exchange reaction studies. And what we need is that medium energy heavy ion beams. And at RIBF, 200 to 300 MeV per nuclear beams are available, while at RCNP, 100 MeV or less. And okay, and another device, sorry, let me repeat again. High-resolution spectrometer with dispersion-matched operation is needed for the study. And we have constructed this Charac spectrometer specialized for the heavy ion charge exchange reaction studies, which means in addition to the high momentum resolution, this spectrometer is designed to achieve a high angular resolution. Okay. Okay, and before going to the, my major topics, let me shortly show you the snapshot from the Charac activities. One is a parity transfer reaction. You know, this reaction has been proposed to search for the zero-minus state, which can be a baseline for our understanding of tensor force effects in nuclear. But maybe you know, it is not so easy to pinning down the zero-minus state by the light ion-induced reaction. But if we use this parity transfer reaction, maybe we can pin down the zero-minus state relatively easily. You know, oxygen-16 has a spin parity of 0+, and the fluorine-16 has a 0-. It is a parity transfer reaction. This is possible only with this combination. I will skip a detail, but when you compare the reaction with the D-helium-2 reaction, in the case of a D-helium-2 reaction, Gamow-Steller state at the ground state is quite huge. It's predominant. But if you look at the carbon-12, oxygen-16, fluorine-16 reaction, it is hindered, and the spin dipole state are more emphasized. this is the power of this parity transfer reaction. Okay, I don't want to go in detail. And the next example is a search for isobector spin monopole resonances via exothermic nitrogen-12 carbon-12 reaction. With this, we use a surface sensitivity and control over kinematical condition as an exothermic reaction. Again, I don't go in detail, but please look at this figure. This is the zirconium-90 nitrogen-20 carbon-20 reaction spectrum, and you can find, in addition to Gamow-Steller giant resonance, you can find a beautiful peak originating from the isobector spin monopole resonance, which is completely missing in the PN reaction. This is due to this surface sensitivity and the kinematical region, exothermicity of the reaction. Okay, now I go to my major topics. And the first physics case is the search for double Gamow-Steller resonance via carbon-12, barium-12 gamma reaction. I am particularly happy to speak on this subject in the presence of Naftali Auerbach, who predicted the existence of this double Gamow-Steller resonances 25 years ago. Okay, what is a double Gamow-Steller resonance? It is a Gamow-Steller resonance based on Gamow-Steller resonance. And it is expected that it exhausts major part of double Gamow-Steller strength, which shows a good contrast to the double beta decay. And you can see, double beta decay is a very slow process, and which exhausts quite a minor part of the double Gamow-Steller strength. You can see this is a matrix element calculated theoretically, and it is something like a 0.1. But on the other hand, this double Gamow-Steller resonance is the matrix element is something like several tens or 100. Let me compare this situation, iceberg, double spin, isospin, iceberg. What we are looking at the 2-neutron double beta decay, it is a quite a minor part. But under the ocean, there is a strong magnitude, which is double Gamow-Steller resonances. And the strength for correspond this part is only 10 to minus third or 10 to minus fourth of the total strength. Okay, then the study of double Gamow-Steller resonance provides us the collective Gamow-Steller strength. In neutron physics viewpoint, it is possible calculation standard of nuclear structure model of beta decay. And in nuclear physics viewpoint, it can provide us an opportunity to study the Mauch sigma tau phonon state. We can answer the question, double Gamow-Steller resonance is a simple superposition of two Gamow-Steller transitions or not. Which means, in other words, it can be a unique test of a Blink hypothesis with spin degrees of freedom. Okay, it sounds to be quite interesting, but so far nobody has succeeded in observing double Gamow-Steller resonance. It is very hardly within our reach. Of course, there are several attempts to discover it. One is a pion double charge exchange reaction. The other is a heavy ion charge exchange reaction. But I will skip detail. But all the attempts turned out to be failures. Why it is? It is because, again, okay, say pi plus pi minus case, and this reaction populates spin flip states only weakly, while the other reaction cannot populate collective states. Let me say, it is not so easy to find a good reaction to populate double Gamow-Steller resonance. And this is a reason that double Gamow-Steller resonance has been kept yet to be discovered for more than 25 years from the theoretical prediction. What we can do? Quite a good idea came to us quite recently. That is based on the use of a carbon-12, barium-12, second zero plus state. It is excited state. by the through other experiment, it is an oxygen-18, neon-18 double charge exchange reaction on carbon-12. We found that the transition strength to this second 0+ state is large compared to the transition to the ground state. Okay, and then the transition matrix element or transition strength is something like a 0.3. This is unusually large in the light ion, stable ion-induced reaction. Okay, okay, 5 minutes. Okay, another good point is that this is an excited state, and it is isomer decay with a lifetime of 300 nanosec, which means that this lifetime is longer than the time of flight in the spectrometer, and we can easily tag reaction channel by detecting delayed gamma ray detection. Okay, I will skip a little bit, and okay, experiments have been performed in the ground radiant spectrometer at RCNP, skipping, and we employ the calcium-48 target as our first physics case. Okay, let me skip a little bit, and okay, this is the energy, excitation energy, energy spectrum. What we got for the titanium-48 final state, and you can find several states which has a forward angle peaking. This is the most forward angle and the backward. Okay, and the forward peaking means that they are monopole nature. Okay, and it is interesting to compare our spectrum to the pi plus pi minus case, and you can. This is the pi plus pi minus case. As I told you, it excites a spin flip amplitude very weakly. It is mostly Fermi nature. And we also find that this double isobaric analog state. And in addition to this, we have observed some bump, which are completely missing in the pi plus pi minus case. Okay, let me compare the single gamma. Okay, this is the calcium-48, scandium-48, and titanium-48. This is the giant gamma-stellar resonance, and this could be a candidate for double gamma-stellar giant resonance. Okay, if you look at the energy difference from the isobaric analog state to gamma-stellar, it is almost twice, although it is a little bit higher than 2 times energy difference here, but it could be a candidate for double gamma-stellar giant resonance. Sorry, maybe I have 2 or 3. Okay, now let me go to the next physics case. It is a tetraneutron state. It is more exotic, which can be proved by helium-8 beryllium-8 reaction, which we have done in Deakin. Maybe it is needless to discuss much about what is a tetraneutron state. It is made of only neutrons. And some theory predict there could be some resonance state. And people try to discover tetraneutron state by pion double charge exchange reaction for how many years ago? Almost 30 years ago. But they couldn't find a clear signature corresponding to the tetraneutron state. And we decided to challenge this physics case by double charge exchange, heavy ion double charge exchange reaction again. Okay, but it is not so easy to excite a tetraneutron state because this figure depicts the momentum transfer and energy transfer correlation. And the tetraneutron is somewhere around here. It is, if we calculate the excitation energy from the helium for ground state, it is more than 30 MeV excitation energy state. It is a highly excited state. Because, still, this tetraneutron is a very fragile system, and if we add a large momentum transfer, it will be easily destroyed. What we should do is that we have to excite a highly excited state in a recoilless manner. With a stable target, we cannot do, because it is always endothermic reaction, and the available region is limited here. But once we use, now we have. Okay, once we use a RI beam induced charge exchange reaction, we can excite a tetraneutron state in a recoilless manner. It is because of the internal energy of a radioactive nuclei. Starting from here, by charge exchange reaction, it can emit the energy from the mass coming from the mass difference. Okay, if we calculate the energy balance in the, we employ the helium-4, helium-8, beryllium-8 reaction, and we show the energy balance in the reaction. The energy needed to excite the tetraneutron state from helium-8 ground state, it will be mostly supplied by the energy difference between the helium-8 and the beryllium-8. Thus, we don't need any momentum transfer in addition to this. Okay, we have performed the experiment at the Sharak. It was spoken by Kisamori and Shimura, and we irradiated helium-8 beam on the liquid helium target and detect 2-alpha, which is originating from the decay of beryllium-8. How the spectrum looks like. It is like this. You can see in the highly excited state, it is consistent with a phase space decay, assuming a two-neutron correlation. But at close to the threshold, we can see strong, not strong, photons. Still photons, it is quite significant. In the level of significant, it is a 5 sigma. And from the experiment, the centroid energy of this tetraneutron state is 0.8 MeV beyond the threshold. But at this moment, we cannot exclude the possibility that it is bound because our uncertainty of the absolute value of excitation energy is more than 1 MeV. Still, maybe another high statistics and high resolution experiment is needed to claim that it is really bound or it is unbound. But in any case, it is a very resonance state with a very narrow width. And through the study of this state, we can learn much about many neutron interactions. Okay, let me summarize my talk. Nuclear spin isospin responses. So far, it has been made mostly with a gamma-stellar transition, and the study have established a firm base. And in addition to the study application to the unstable nuclei, the extension to high multipolarity, higher tone, and much form state is quite important. It will bring us with knowledge on the new aspect of nuclear structure and nuclear matter properties. And in doing so, heavy ion charge exchange reaction is essentially important. And today we have shown some result of from the Sharak and the ground Leiden, a parity transfer reaction and the exothermic reaction, but we show the new result from double gamma-stellar resonance and the tetraneutron states. Let me close my talk thanking my collaborators. I should thank especially the young collaborators, which contributed much to the experimental program, and thanking all of you for the kind attention.
Thank you very much. Very, very exciting new results. Thank you.
Thank you very much.
So, questions to Asaka-san?
Yes, very nice work. I like to understand if you think that you have some problem with the excitation of the projectile.
Time by time, it could be the problem. But in the case of carbon-12 beryllium, we can tag by the gamma rate.
Yeah, but when you don't tag,
in the beryllium case, we can detect 2-alpha, and we can make an invariant mass, and we can be free from the
excitation of the project. Yeah, because this could be a problem.
So, one more question?
Sure. There was this nice comparison between double beta decay and the double gamma-stellar and the iceberg, but I was a little worried because of the Titanic You don't understand that? You don't know what happened to the Titanic?
Okay.
We can fly.
Well, hopefully there will be no Titanic this time. So, Okay, so let us thank all speakers for perfect timing, actually. An excellent session. And now, Professor Spitaleri would like to tell us the secret of tomorrow's trip to Etna.
Many participants asked about the trip of tomorrow. We leave at 2 o'clock from after the lunch. We go back at 19. Okay, it's about, depend on the traffic, but the time scheduled is at 7 o'clock post meridian. We leave from Etna, okay, to Catania. When we arrive in Catania, depend of the traffic. Normally is 1 hour. At 20 we'll be here. This is no chair for this this time. Okay. A problem is this, all of this. Temperature is minimum 9 degrees, maximum is 17 degrees. This means that is necessary at 8 o'clock when you leave from Catania to here, that you have some jacket, not elegant jacket. And please, not light shirt as this, no. If you have, is better, because if you like walk in the volcano, if you can stay in the shop, there's no problem. But if you have, but this was right in the announcement. In that announcement, there was this extraction. Please? You can walk, but we arrive at 1,092 meters. Okay, is a minimum volcano. We have many 3-4 craters. Okay, at this level, there is one that we need to walk for. 200 meters, but the gradient is very high. Okay. If you prefer visit the crater close the stop of the bus, it's better. It's better, not a conditio sine qua non. Okay.
So, whether there's a guide, whether there will be some guide.
Well, you know Etna? Etna. Okay. But there we have a guide with us. Okay. But what this is not important. It's important that we arrive in time to the bus, and because we must leave at 2 o'clock. Okay. All the organization tomorrow is important for the chairman that will stop exactly 1 o'clock because 2 o'clock we must leave. The bus will, the bus tomorrow we have exactly the position of the bus. We asked the authorization to enter the bus inside the university city. But in this way, exactly close to the department. In different case is out. Today the bus is 8 o'clock. 8 o'clock. No, oggi.
the dinner for the advisory committee. You said that there will be, tomorrow is going to be
Okay.